For those who don't know me, my name is Lukas Zilka, and I'm a PhD student here with Filip Jurčíček in the Department of Linguistics. We are a Dialog System group, and we are interested in interesting problems in spoken dialogue systems. So in the beginning, I wanted to make a short advertisement for our system, which is running on the number 800-899-998. For Czech people, this will provide you with information about transportation directions in Prague. So please call. So that's the introduction. So today I will tell you about my research here, which is about learning to find out what the user wants. It's in Dialog System, and I will particularly talk about my new model, which is LSTM Dialog State Tracker, which is a special kind of recurrent neural network suitable for tracking what the user wants in dialogue. So also please, if this is too basic or anything I'm saying is too basic for you, please shout and I will skip it. Also, if you have any questions, feel free to interrupt me at any time. Dialog System is a system which accepts some voice. Then, actually, it's composed of some components. First component of Dialog System is something that we call automatic speech recognition. Next component. So the automatic speech recognition takes voice and produces text as the output. Next part of Dialog System is Dialog State Tracker. Which takes text and some history of the dialogue. You can imagine all previous texts that happened in the dialogue before and produces some structured output. Which is suitable for another component which is called Dialog Manager. And based on this structured output, the Dialog Manager thinks and tries to generate a sensible output of the system. And so that's like, again, text, which goes to the text-to-speech unit, which produces voice again. So this is the elementary pipeline in our systems that we are working with. And on an example, you can imagine it as like people having conversation. So one person is saying like, what would you like? What would you like? And the second person says, I want not Chinese food, but pizza. So the system says, we do not serve that. And so the user says, okay, so burger, please. So this is a classic scheme of dialogue. One person is saying something, the other one is replying. And where our system fits, it's exactly here. So imagine this person is a computer, actually. So it has a screen. And so when the user says, I want pizza, we need to take that and produce this reply. We don't serve that. And so I want pizza goes here, and we don't serve that, goes out of the system. And so now I want to focus on the component that I'm working on currently and what this presentation is about. and that's a dialog state tracker. So in this modal dialog, if you want to look what the dialog state tracker is doing, it's trying to fill in a structure which has one field. It's called food, and it's interested in what its value is. So in the beginning of the dialog, at time 0, the food has no value, so let's say 0. As the user says, I want pizza, so now the system should know that the food is pizza, and use that in the dialog manager. And after that, like after the user says, okay, so burgers please, the food is now burger. Right, so you can see that the dialog state tracker is taking the natural language input and transforms it into a structured output, which we can use well in programs, because we don't know how to work well with free text in programs. And so let's see what's next. So in dialog state tracking literature, the food, it's not called field, but it's called slot. And generally, the dialog state can have multiple slots. So it can be food, location, price range. It depends what domain are you in. I'm talking now about a restaurant domain, about providing information on restaurants. So these are some informations that users will tell to the system, and these are sensible to track. So you can imagine mathematically, a dialog state tracker is a function that maps a dialog history. So this is a space of all dialog histories into some value. So tracker for slot food does this, right? It takes the whole history, for example, until here, and produces the value pizza. So my model is a model of this function, and it's a recurrent neural network, and we will get to this in a minute. Okay. So is it clear so far? I think so. Now I want to show you one work that one guy from Google published last year. His name is Ilya Sutskever. And it was a great inspiration for my work. That's why I'm mentioning it. He's a guy that's working in the field of deep learning. And basically, what he showed is that he's able to train from data a complete translation system. So for those of you in audience who do machine translation, sorry for my elementary not knowledge of machine translation, but I want to demonstrate why I think this model is important. So traditionally in machine translation, you have some source text, which you feed a pipeline of I don't know how many components, and but like there are a lot of components, and at the output you get the translation. Each of the components, I think, are typically trained independently and have a lot of parameters that the researchers have to tune manually to produce a good system. I'm sure there are a lot of automatic methods, but it's quite complex. What the guy, Ilya Sutskever, did, he built a simple model. He discards all this. He builds a simple model that accepts this text, produces the translation, and the only parameters that the model has are parameters of a recurrent network that he's using. So what that means is that he's able to find these parameters simply by optimizing an objective function. So he's looking for some parameters theta, which minimize some function L, and the function L just expresses the quality of the translation that his model produces. So I really like this thing that your system is optimized as a whole, and it's optimized from the data that you have, and you don't have to like tweak the system now and then, but you get like the whole thing. And how his system works is very simple. So if I have a sentence, hello, my name is Lucas, and now I want to translate it into Spanish. So he reads it word by word. So he takes hello, feeds hello to his model, and the model builds some vector representation of this word, of the whole input. And in the next step, it looks at the next word, my. And again, he feeds these words to his model plus the hidden vector from the previous state, and gets next representation, and so on until he gets to the end and finds the representation for the whole sentence. So in this vector, this can be like 50 real numbers, is represented the whole information from the sentence. And so he calls this part of the system the encoder, and it just like encodes the sentence into this vector. And after he's done that, he takes this and sends it to the decoder, which is another recurrent neural network. And so it basically looks at this hidden state and feeds it some start token, and it produces word. So in this case, for example, hola. And it continues. So it transforms this hidden state into something different, sends it to the next step, also sends this hola to the next step, and produces a next word from the translation. So it's like me, I think in Spanish, I don't know. And it sends me to next step, sends the hidden state to next step, and produces llamo, and so on. So it basically generates the whole sentence out of this single representation of the input. So he basically showed that recurrent neural networks are able to learn mapping from sequence to sequence, just given the data that specify how this mapping should work. And actually, he's been able to, like with little tweaking, he's been able to beat the state of the art in machine translation. So for my model, I thought it's the same thing. We have some sequence of input words, something what the system says, something what the user says, and we want to translate this into a value for slot food. So that's the idea. I want to take this network and teach it this task. So I wanted to also say that I don't know. Is everybody familiar with like optimizing this function, or do you know the idea how to actually find parameters of neural networks, or do you want me to give a short introduction? So who's not familiar with the optimization? I mean, generally stochastic optimization. So just there is like very simple mathematical idea that if you have arbitrary function, for example, function L, and if you take its derivative, or the derivative points to a region where the function has a higher value. So if you want to minimize the function, you need to go the opposite direction. And this is what happens in this training. In looking for theta, you basically have some original theta, and you want to find a new theta. So you take the original one and subtract from it this derivative, and this way you will arrive to new theta, which has a value L less than what it had before. And if you do it a lot of time, you arrive at configuration which is optimal for your data, and you have trained model. And okay, so for it depends how you look at it, but technically it's two networks, but they are optimized jointly. They learn jointly. So you can imagine this network has a set of parameters theta e, and this network has a set of parameters theta d, and but they are together in like arguments of this loss function, like e d, and you try to optimize this. So you, yeah. It can be Glasgow, I think, but I'm not sure if it would be possible to optimize. So I think what they used was the cross entropy of the outputs. So you know they have pairs of like source text, translation, and they for this pair they express this little L function, which looks which looks how the, so if we say that this whole network is function f of source and produces some translation, so that's this. So they look how this function compares, how this compares to T1, and they because I think this would be too technical if I went to details. You basically compare the cross entropy, the distributions that you get here from the words, and you try to maximize the probabilities of the correct words at the outputs, and you encode it in your L function this way. There are various ways you can do, but I think they did this. So it depends what you do. What I wrote is a bit of simplification. So what people usually do, people usually divide their training data into batches and express this L function for the whole batch. And they do it because it's computationally effective, because like doing it one training example after each other would be theoretically the best way, the optimal way to do it, but because computers have some architecture that likes a lot of data, they do it with these batches. Is this clear? I forgot to ask. Is it? Yeah. Okay. So let's delete it. So now if we go to my model, I use data from Dialog State Tracking Challenge to find my parameters of the model and where I do the evaluation. So DS Dialog State Tracking Challenge was a challenge organized last year where different teams from the world competed in providing this component into the dialog system. So it's about 1,500 training examples, then 1,500 dialogues. Each dialogue is composed of what we call turns, and one turn is the question and answer. So like this dialogue has 2 turns because the system asks and the user replies. That's one turn. And so in this challenge, there were 1,500 dialogues. Each had about 10 turns. And the dialogue was in the domain of restaurant information. So people in Cambridge asked like where they can find cheap Chinese restaurant, or where they can, or what's the price range of the restaurant, blah blah blah, and so on. So this is the data that I'm using, and basically I want to make very simple model. So I'm not doing any pre-processing of the data. I just put to my training data the individual words. I want Chinese food, and ask the neural network to consume it. Now I forgot to explain what is recurrent neural network, but I think you might have been able to grasp it from the last example. So I ask my recurrent neural network to eat this sentence word by word. So again, it's building some representation, which is traversing through the whole input. And after consuming it, in the DSTC data there is a label, and it says food Chinese. So at this point in dialog, I take this hidden representation and for simplicity, I now don't do anything fancy as Ilya Satskever did with the decoder network, but I just put it into softmax, which gives me a distribution over all possible values for food, and I want to maximize the element of this softmax vector which corresponds to Chinese. And that's it. But this is not the end, because then the dialog continues and the user says, okay. So the system said something, and then the user says, okay, give me location. And so again, this hidden representation needs to go further and go through the whole dialog, even though the labels are for particular moments in the dialog. And so simply what I do, I just express my loss function and find the best parameters. So my loss function is given by the idea I just explained. I hope that's clear. And so I find my parameters again by the same method, stochastic gradient descent, and sorry.
Your network outputs the class category. Because in the first example, it outputs foods equals Chinese and distribution over all the foods.
Yeah.
And after the second sentence, it outputs the distribution over location.
No. So it again, you go to softmax, and it's the same. So it outputs distribution over foods. Because like in this sentence, no food was mentioned, so it didn't change. So like here, the softmax should give me food is Chinese, right?
Okay, so if you have other response like location and expansion and
Actually, I have more softmax. So this softmax is indexed by food. This by yeah, exactly. Yeah. So the food stays, but here the location would change. So, yeah. This could be another slot, for example, location, or I don't know, price range, or whatever. All right. So. Yeah, so let's look. So I started training, and I got some results which were very encouraging because they were like 7% better absolute than the best state trackers in the challenge. But I was happy until I found out that I failed to. Actually, I made a mistake in the data processing because I was using the gold transcriptions. So I was using what the user actually said, but that's different than what automatic speech recognition software gives me, because so that's why I was getting this good performance. So now things changed because I no longer have just like words as input, but I also have some probabilities that this word is correct, that the automatic speech recognition is giving me. And so the task now is a bit harder. You need to like have this, teach the network to interpret also these numbers that are attached to the input. And I don't know, actually in literature I haven't seen people doing this, so I'm trying to, but so far it's giving me worse performance, which is like maybe 10% worse than what I was getting before. So it's interesting thing how to teach the network to interpret the probabilities on the input. And one interesting way, I think, how to do that is so-called curriculum learning, and that is you build your training set in a way which gets more complex. So it's similar as if you teach a child. you first teach him some simple things to do, and then increasingly add, as it learns, increasingly add complexity, and then you are able to teach him the whole, the whole problem. So, for example, in the beginning, I will give it just like one word, and for example, this Chinese, and attach some probability to it, and ask it to predict Chinese if this is less than 0.5, and predict like what there was before if this is below 0.5. Therefore, like teaching it to pay attention to these. And so I ran some experiments, and it really seems that the network is able to teach this way increasingly. So if I just give it the complex data right away, it doesn't learn anything. It stays like 30% accuracy. But if I first present it like with the one length input, and then like 5, and then more dialogues, and so on, it gets to the place where I want it to be. But so far, I haven't completed the whole learning process, so I don't have any results. Okay, so this was about my work and some other relevant aspects from the literature that I wanted to show today. So the last thing that I want to tell you is some practical recommendations that you might want to do if you do something with deep learning. And that is, first, there are some toolkits which help you with this learning process because they are able to automatically take derivative of your function. And these toolkits are Theano and Torch. There are some other emerging, but these are the one that people use the most. Another lesson that I learned is that theory matters. So, like, if people tell you your data should be mean 0 and unit variance, they really should. Otherwise, the network will not learn and will seem to, not move anywhere. Also, there is an excellent article that I think everybody who's doing anything with deep learning should read, and it's from this guy, Satskever. It's actually a blog post. It's called A Brief Overview of Deep Learning. Basically, like, the first part of the article is the usual, prizing deep learning, that it's so good with images and stuff. But the second part is some real practical recommendations. And basically, the conclusion is two things matter when you apply deep learning, and it's the learning rate of your algorithms and the random initialization. Because when you have the recurrent neural network, you need to start somewhere, and that somewhere needs to be numerically stable in order for the rest of the mechanisms to work. So, like, pay attention to learning rate and initialization. And the last thing that I want to mention is this disparity between having clean code and doing new stuff. So I found that if you are really pedant to writing your code clean and testing and like being really careful and not cluttering your code and like doing a lot of refactorings, it really pays off, because you spot mistakes much easier. And in research code, if there is mistake, it can lead your whole research to fail. So that's basically all. If you are interested in some of this stuff, I have some code, and I invite you to come to me to maybe collaborate on something, or I can help you with this stuff. So please feel free if you like this approach to natural language processing or whatever. So thank you for listening.
Well, thank you for a good talk. And I have two questions. One is technical. Which tool did you use at the end for this research?
Which what?
Which tool was it, Theano or Torch?
Yeah, so it was Theano, but I'm not sure if I would use it again. I mean, it's all nice, but when I write code, I like to have it under control. And in Theano, there is a bit of black box that's introduced into your code, and it's doing this differentiation. And you know, you cannot be sure what it's doing, and you cannot control it so much. So I think next time I would try Torch, just because you know it's more transparent. But Theano works very well because it's doing some also optimizations. So you can write your code or your equations normally, and it will like optimize it so that it's numerically stable, and it automatically can run it on the GPUs and make it faster. And
And did you run it on the GPUs or on CPUs?
So I've tried GPUs, but because my data are quite small, I'm using many batches of size 1, and that's not very good for the performance on GPUs because they typically require many batches, at least like 128 examples to improve the performance. So I'm doing CPU.
Okay, thank you. And the second question is, in the dialog state tracking challenge, there was one additional semi-supervised task when you provided only like 10 example dialogues for the broader domain and a lot of test data. So are you attempting to solve this task as well with this network?
So is it the STC number 3? Or?
Yeah.
Yeah. So I'm not currently thinking about this very much because I'm first trying to get it to work for the other data. But I will definitely try if I succeed in this, because I think it could work because if you know I'm now using words to process the dialogue, but if I use letters and then if I generate letters like for the value, like food, I ask the recurrent network to generate letters, then I think it has to have some good generalization and ways of remembering a piece of the input. Like, you know, it will not, you know, see pizza and remember, okay, I should produce pizza, but it will remember the sequence of letters which stand between, for example, want and the end of sentence, and it will learn that it should produce it in the slot food. So I'm hoping that this could be a nice approach to try to even tackle this task. To force the network to learn more general thing.
Okay, thank you very much.
Okay, now I'm not familiar with the DSTC dataset, but you want to learn new slot values, not new slots, right?
Yeah.
Okay.
So you have, I don't know, little training data for the new slot, and oh yeah, sorry, slots, not slot values, I think.
Okay, so
because,
like you are still learning this. You know that there is slot food, but you want to add something like Brazilian food, which you never seen before.
No, actually, what the DSTC3 is about. So I mentioned there is like food location and price range for the restaurant domain, but like in the DSTC3 they broadened the domain. So you can ask not only about pubs, but also about theaters or something. I'm not sure what the exact thing is, but like you will have another slot, which is, for example, like has television, or like the user wants to specify that it needs to have television or be non-smoking, and so you need to be able to learn new slots from little data to be successful in the
So, but basically, you are not discovering the slots, but
yeah, you are given the training data for the slots, but just a little.
okay, I see. Thanks.
If you have this representation for the sentence from which you can predict slots, what do you actually need the slots for? Because the dialog state apparently can be represented in this funky vector. So what is the use of the individual slots? I mean, besides that dialog state tracking challenge was evaluated on the slots, but
yeah, so hopefully we will not need, the state as I presented it here. So hopefully the dialog manager will be able to leverage this representation of the input, but we don't have currently ways how to evaluate that and how to use it. So I think performing well on the STC is the first and required step to be able to take this architecture and this idea and employ it further in the dialog system. Maybe it will make it more versatile or whatever.
I would like to know what representation of words you used to feed the network, the input vectors, I mean. Is it 1, 1 in the vector and otherwise zeros, or is it something word to vec or other approaches?
Yeah, so I'm training my own embeddings, and the embeddings are hidden in these parameters. So a part of the parameters are the word embeddings, and therefore, like, I don't know, word want is just like a vector of, currently I use 50 dimensions, and I learn these parameters along with the rest of the parameters for the network.
Mm-hmm. Thank you.
I mean, there in literature, some people use these word2vec pre-trained word embeddings with good success, and they improve their accuracy immediately by 5%. But I tried once, it didn't seem to help so much, and plus it's like 300. So I'm keeping this idea to do it like at the end before publication. I can improve the accuracy, but I mean, it's not required to have these vector embeddings if you want to train such networks.
Mm-hmm. Thank you.
So you are asking about the properties of the representation, or? To be honest, I have no clue what the network has there currently, but eventually, when this works, I will definitely investigate it, so I can maybe send you some updates. But currently, I don't know. I try to visualize the embeddings for the single words that I get, and it makes sense that like some words are clustered together, like the ones that are about food are somewhere in one area, and the rest is somewhere else. But I don't know about the whole sentences, unfortunately.
Okay, so I'm curious.
Thank you.
Thank you very much. And the next talk, next Monday, we are going to go to a more realistic part, I should say, of the So thank you very much. See you.
Thank you.